Okay, let's reconvene, and we have our panel today of, in no particular order, Dylan Nelson, Mary Putman, Sijing Shen, and Cameron Hummels. So I'm going to look for hands to start off with, but we had a very nice talk and definitely a lot of questions. Well, then in that case, I'm gonna take the prerogative and ask about the nature of jets to blow, for the AGN feedback scheme, like in that mode of 10 to the 13, 10 to the 14 solar mass halos, groups and clusters, where you have to blow bubbles and have spherical bubbles. And you said that the jet feedback needs to be placed closer to make it more spherical. And I wanted to hear more about that because I think about radio jets and FR2 objects and how that correlates with observations.
Yeah, so it's a great question. So in particular, what the observational connections? Yeah, so keep in mind that what the radio is showing you is largely the jet fluid itself. So the relativistic particles, the synchrotron emission from relativistic particles, and not necessarily the cocoon, the shocked gas, which so there's there's a few nice observations which show that connection clearly, show a jet coming out, and then where you can actually in the X-ray see the bow shock. But there's but I think your point is a good one. In some cases, the jet seems to propagate for long periods of time. In fact, I was looking. Let's see if I can dig it up. But an amazing image of a four-way cluster. It was some Max object. Mark, I'm sure, knows the number of a four-way cluster. The interpretation was the four-way cluster collision, and there was a whole series of jets, including one which was just straight as an arrow. And so whether that was, I was surprised to see that because I would, normally jets are their momentum flux is not that high, so they take a while to drill through the CGM.
Yeah. Yeah, I wonder if this is, for those that do drill through the CGM or the IGRM, intergroup medium, or ICM, I wonder if that radio mode goes, if you call that radio mode, if that goes on at high redshift as well. I mean, people invoke it at lower redshift when you have a hot halo, but as a way to eject baryons from groups and clusters, I wonder if that could be effective at high redshift and if that can be observed. But I'm not sure if we'll get an answer to that here. But does anybody else have any comments on that? I saw you. Yeah, you won.
I don't know what can be observed, but one thing to keep in mind is that at high redshift, black holes are also smaller, and the absolute accretion rate just in the unit of solar mass it tends to be higher. So it's less likely for a supermassive black hole to be doing the radio mode feedback. So it's more likely that the more massive black holes are doing the quasar mode feedback. And of course, there are radio loud quasars, but it's not what you're thinking about, really. So there might be some, but probably not that many. And I have no idea what we can see at high redshift. Just a thought. Yeah.
Great, and I'm going to try to get the panel involved here. I think I'm going by voting here, so I'm going to read one from Jess. what controls the CGM galaxy connection? And she is interested in what observations can constrain these three different scenarios that you talked about, rather than bulk column densities, gas kinematics of different phases might be able to discriminate a little bit more. And I actually do not recall the three phases. So maybe Jess, if you want to speak up and clarify that question a little bit better.
Yeah, sure. There was the like precipitation, pressure profiles in the supernova dominated regime. There was the mass loading, the kind of what's driving the pressures, and then otherwise it's cosmic ray pressure supported, right? And so one of the things I've been really interested in from simulations that I haven't seen so much of yet is what are the predictions for, the kinematics of the different, gas phases? Because that is something we can constrain observationally and something that hasn't really been probed as much as the kind of bulk column densities. And in these cases, it's not clear that kind of column density ratios or the kind of stuff that you get from column densities, like a loose estimate of the pressure, could actually discriminate between the scenarios. So I don't know if any other observers are here and want to weigh in on that, or if any simulators who think that, like, for example, I guess Mark admitted that the kinematic predictions from the precipitation models are actually not super well constrained. In a reply to me, I know Irina Butsky is working on kinematic predictions from like cosmic rays and low and high ion kinematic correspondence in simulations. Maybe somebody wants to talk about the mass loading scenario, but it'd be really nice to me to hear about what people think are ways forward for answering these questions.
I guess I can comment on, so there are so many threads of conversation going on. Jess can ask me questions over here and people are speaking them over there. And, we're taxing everybody's neurons. In principle, there should be ways to link the phenomenon of precipitation to kinematics, because precipitation does require and does produce some motion. And the kind of practical issue is that the amount of precipitation you get might be exponentially sensitive to the amount of disturbance. So you can make a kind of an undisturbed model and say, well, if you don't have much disturbance or precipitation, this is the kind of kinematics you would get. But then as you start to disturb the medium and get stuff condensing out, there's a threshold at which you should expect that to start to happen. In the 2019 paper on the Milky Way that I wrote, it actually compares to your 2016 data. And tries to show that there is a correlation between the breadth of the O6 and the excess column of those broad lines that actually qualitatively.
I know, and that has always bothered me, that trend, and maybe other observers want to weigh in too, because you won't detect the broad weak stuff. So the fact that that trend exists could easily be an observational bias.
And so I guess what I'm saying is there's simulation work yet to come on how to put that on a more quantitative footing.
Good.
Could I respond to that? Since, at least in the initial paper on this subject, we actually showed that what you're saying couldn't actually be true. So we could construct synthetic spectra of broad, shallow features and show where in this diagram you'd become incomplete. So it is true that there's a regime in this diagram where you won't be able to measure lines, but it's well below where the locus of points are.
Good.
Okay, well, Cameron has his hand up. He's a member of the panel.
One thing that ties into this question from Jess, and one thing that I worry a little bit about is, obviously the work done by Mark and Pratik and a variety of different people on the subject of precipitation makes sense, but it still seems like we don't have clear indications, at least in the cosmological simulations, of seeing precipitation actually occurring. And the observational implications for this, it doesn't seem like there's strong confirmation of this, which is why Jess is asking, presumably part of the reason Jess is asking the question that she is, like, what's the observational signature of this, so we can make sure that this is actually happening? Because yeah, it makes sense. It's a really good explanation for this, the quenching and the cycling of gas through the halo and star formation cycles and that sort of thing. But I think it's not a foregone conclusion that it actually is happening, because we don't see it in all of our simulations and because we don't have necessarily observational follow-up on it. So I don't know, maybe that stirs the pot a bit, but I'm interested in getting the take from other people on the panel.
And panel members can speak up. They don't have to raise their hands. Oh, we have Sijing. Good thing too. Yeah, go ahead, Sijing.
You're on mute, Sijing.
Yes. Okay. So regarding this question about the kinematics and what Jess just talked about, the correlation between the column density and the kinematics of the absorbers, in simulation we seem to be able to reproduce it no problem. Of course, I mean, we haven't really investigated what is origin of those oxygen 6 absorbers, because it seems to me that it really depends on actually the simulation. It depends on how fast the CGM is able to cool and how fast is the feedback, which we only investigate supernova feedback, is able to inject energy. So I don't know. I mean, I have to say I haven't really investigated the precipitation model, but it seems like it's not a big trouble to reproduce that kind of kinematics. But I also read Dylan's recent paper, which talk about the T cool over T freefall, and Dylan, you probably want to comment on that, because you investigated and we were reading at your paper, and you seem to say that it is not always satisfied, not always the case.
Actually, yeah, I wanted to bring up a related point about the kinematics, because I agree with Jess's sentiment that the motion of the different phases is very interesting. And one context where I think that's definitely true is for the magnesium-2 absorption in the ellipticals, so around the LRGs, right? And we always, I've often read in observational papers this buzzword of subvirial motion and what this could mean, and the fact that the absorbing MG2 clouds seem to be moving slower than would be expected for rotation or dispersion in a given halo mass, that this is often interpreted as a hydrodynamical drag effect. So these are very cool ideas, and I think we should push more on this also from the simulation sides. But I admit, in the paper we did about the magnesium-2 clouds, we didn't yet get to kinematics at all, but this is for the future.
Evan, go ahead.
Hey, thanks. I'll turn my video on since I'm talking. So I actually wanted to kind of echo Cameron's question and maybe pose it to the simulators, because we had a lot of conversation, early on in this workshop about the sort of parameter regimes where precipitation works versus condensation, et cetera. Most of the models of precipitation that I've seen numerically have been quite idealized, but it's not obvious to me why there should be a numerical resolution requirement to see precipitation. So have any of the folks who have done these precipitation models demonstrated that if you just go to too low resolution, you can't see it? Because it seems like that's the question that you would need to answer to connect those to the CGM simulations.
So partially in response to this, Evan, in the Tempest paper from 2 years ago, suggested, we don't see precipitation occurring in the Tempest paper, which is, consistent with foggy, consistent with the surge stuff that Freke has been doing, the enhanced halo resolution in the CGM. So we have very good resolution, 500 co-moving parsec spatial resolution in the halo. We don't really see like full-on precipitation where you've just got spontaneous cooling that's occurring in the halo. And so that's why I kind of brought this up. Like, we're all talking about precipitation like it's a done deal, but we don't really see it. We see it in idealized simulations. You know, Drummond has demonstrated this in some idealized simulations. And then on the larger halo masses like cluster, yes, we see it there. But for like Milky Way mass halos and lower, we don't see precipitation happening in the cosmological scales, the cosmological simulations. And one thing that I proposed is simply, in a cosmological zoom simulation, like fire, like tempest, like foggy, like whatever, your domain is moving relative to the background of, because your domain sits there and a galaxy might move through that zone. And so you get some numerical diffusion from gas that's moving across those the cell structures very quickly. So you might get some loss there that doesn't allow you to allow the gas to be resolved at high enough resolution where the cooling would take over. But that's the only argument that I can see that's tied to the resolution. I don't know.
Sorry, I mean, I think I posed my question wrong. I wasn't asking the people who do the CGM simulations who don't see it. I was asking, you know, like Drummond in his CGM simulations where he sees precipitation. Is it the case that if he degrades the resolution enough,
does it go away?
He doesn't see it anymore?
Yeah, exactly.
That seems like a simple question to
yes,
answer,
absolutely.
right?
Go ahead, Mark. Go ahead, Mark.
I have a bit of a philosophical point to make. So, as I said a bunch of weeks ago, right, there are two kind of different complementary aspects of this idea of precipitation. One is how dense can I make, or how high pressure can I make the ambient medium until it starts to disintegrate into rain, okay? And I think from an observational point of view, it's been established that that does place a pretty good upper limit on what the density of the ambient CGM can be. So that part of kind of precipitation, I think, is kind of observationally well supported. Then there's the question of, to what extent can precipitation produce cold gas that you're seeing? And I think the semantic problem we have there is an idealized simulation. Everything's so idealized, you can kind of make a disturbance and then something comes out and you call it precipitation. In a cosmological simulation, there are many sources of disturbance that you can then say, oh, well, that's actually stripping. Oh, that's actually outflow. And so you don't call it precipitation because you have a more specific explanation for the source. I think originally people thought maybe you could have very small perturbations grow. Since then, we've got a better understanding of the conditions under which you have precipitation. We understand you need some disturbance. And so in cosmological simulations, you simply call it the disturbance. And I think that's kind of a semantic issue we're grappling with. And so, you know, to sum up, precipitation as a limit on what the ambient medium can be doing, I think is becoming kind of better understood and supported. How much the gas supply is something that can be called precipitation is a hard conversation to have for these semantic issues.
But what if the disturbances overwhelm the thermal instability in the gas because they're slammed by, you know, outgassing from a neighboring galaxy or stripping or whatever? That in a cosmological simulation, that's treated more correctly than in an idealized simulation, and that could overwhelm the like ambient level of precipitation that would occur in its absence, and maybe that means that precipitation isn't actually occurring in reality, or at least not at the level that is predicted.
I think we still have to sort out our semantic issues here.
Yeah, we have some hands up, and that's Sijing has her hand up again. So, and Greg, you don't have to raise your hand.
Well, can I just, I mean, if Pratik or someone was going to try to answer my question, I'd love to know, because there are a bunch of hands up and no one has answered it.
Yes, I can answer this question. So, so in the idealized.
Oh, we might have lost critique for the moment.
Right at the critical moment in critique, you have frozen. We were about to have an answer.
If it's okay for me to jump in, the answer to Evan's question is yes. So if you have very low resolution in the idealized simulation, you will not resolve precipitation, just because when you have the perturbation and you have some high density, low entropy material, and you don't have the resolution to resolve that, then it's not going to precipitate. It's just like that. Yeah.
Which is great, because then you could put a specific resolution limit that you need in cosmological simulations to see it, right?
Exactly.
But I 100% agree with Cameron. In cosmological simulation, you have all these other sources of perturbation, or you guys don't think about them as perturbations, but rather like real things, like galaxy streams moving around that will give you very large perturbations. So you probably don't need the kind of resolution you would need in a class, for example, an idealized cluster simulation to resolve precipitation or just cooling condensation.
Yuan, can you convert this into a number for us? So in a month.
Yeah, right. I still want to know what that number is.
This is very important.
To hit it.
I'm sorry, I can't.
I think the point here is that if we quote this number in kiloparsecs for the Milky Way halo, and if cosmological simulations already satisfy this number, but we still don't see precipitation, maybe this is where Evan is heading now. And also, so the number is important.
Okay, well, we'll work on it.
Sorry, I haven't worked that very much on this, but I just have a question. Can we separate what is the condensation from other kind of shaking of the gas from outflows or from RAM pressure, or what is the actual pure precipitation from instability? Can we separate these kind of processes in simulations, or is it one is going to be completely dominating over the other? Or is it also depends on the halo environment? Maybe more quiescent quenched halos, we see more precipitation, which is what people demonstrate. But in Milky Way sized kind of galaxies, can we split the two? Is it possible? Can we tell the difference by looking at energy injections, or I don't know?
I personally think there's an important distinction between cool gas seeded only by hot gas and a disturbance in the halo. So like an Aegean jet that creates cool gas in a halo, that I would call precipitation, and cool gas that's seeded by other sources, like a satellite falling in or winds that are cool that are moving out, right? That's sort of, we try to distinguish between precipitation and condensation while acknowledging precipitation will create condensation. And so that was, that source of my question was for these precipitation only models, is there a resolution criterion that you need to hit and maybe is already being hit in cosmological simulations?
Yeah, I think that's an excellent question. Sorry, I just want to say one thing, which is I think it is really important to go and determine, what is the exact source of the condensing gas. If you have some cold cloud, where did it come from? Did it precipitate out? Was it condensed by inflows? Was it stripped? But I also want to stress something that I was trying to get across in my talk, which is that if what you're interested in is the overall principle, which is setting the halo, right? So the halo properties, then maybe that's less important, because the point is the regulation aspect. That if the hot halo the hot halo adjusts itself such that whatever source of cold gas is sufficient to condense out and to, or whatever the source of the cold gas is, whether it's classic precipitation purely from the hot phase, or whether it's it comes from low density filaments which come in and have slightly lower entropy, and so then are easier to condense out, or whether it comes from actual condensation of cold clumps which are thrown up and then accrete more mass and then come down. The point is that your hot halo properties are at a certain point, this becomes possible. All of these mechanisms start to operate, and then that's when you establish this feedback procedure. So I think it's both important to understand the individual contributions to the cold gas, but I also think it's useful to just think about this in a very broad brush picture. What are the hot halo properties, or the halo, whatever property it is which is setting the structure of the halo, if it's thermal pressure, for example, how does that, what state of that is required in order to allow cold gas to form by whatever route?
Here, go ahead.
Okay, so this is perhaps an educated guess. I'm curious what people think with regard to Evan's question about the resolution limit. Something that I found in a series of cosmological simulations that I ran, enhancing the resolution systematically in the intergalactic medium, and finding a phenomenon that is somewhat perhaps reminiscent of precipitation, although in a very different context, formation of condensation of cold clouds in the intra-pancake medium, if you will, is that I only saw them beginning to form if and when I resolved the cooling length, so CST cool, but not of the cold phase, not of the 10 to the 4 Kelvin gas, but of the hot phase. Is that not a reasonable resolution requirement that might answer Evan's question? Do cosmological simulations resolve CST cool of the hot component very well?
I mean, this is something that we looked at in Tempest, and yes, we are able to resolve the cooling length of the hot gas reasonably well for, I think, most high resolution cosmological simulations. Certainly the ones that are enhancing the resolution in the CGM, but certainly we're not getting close to being able to resolve the cooling length of the cold gas. And I thought, according to Mike McCourt's paper, kind of seminal paper from a few years ago, the suggestion was that you really need to be able to resolve the cooling length of what the gas would cool to be the size scale of, as opposed to the hot gas.
No, I certainly agree. If you want the results to converge in terms of, covering fractions or cloud sizes or number of clouds, yeah, I agree. But if you just want to see something that you could call precipitation, you see the formation of cold condensates that might not be converged or at their final size, it's enough to have the cooling length of the initial cooling medium be well resolved so that you can get initial separation, even, into cold clouds, again, may not be converged. But so you say that in the Tempest you do resolve that scale well, and yet you don't see any precipitation.
Well, so this brings up something that we talked about earlier in the meeting, and Greg mentioned just now, and that is like, so what do you define as true precipitation versus condensation? Evan was touching on this point, and one thing that we do see in the Tempest simulations is when you have a cold filamentary inflow coming in that's kind of seeding additional cooling on it, we do see that. And I have a really nice movie that demonstrates this that I showed a couple of times earlier in the meeting, but I don't see it. Okay, maybe it just is about me needing to reprogram myself about what precipitation actually means. Because when I think of precipitation, I think of like this beautiful static hot medium that's metal enriched or whatever to cause its cooling time to be much shorter. And then spontaneously it just like turns into cold gas and starts flowing into the galaxy. And I have seen this in idealized simulations, that this picture can be, manifested, but that's not the kind of picture that I see happening in an actual cosmological simulation where, your galactic halo is moving through the IGM and it's getting slammed by this and that, and there are outflows coming out. It's never that nice, quiescent picture of just like this stark creation of cold gas in the outskirts that flows in. But again, that might be an oversimplification of what happens in reality.
But actually, Cameron, I also wanted to, you mentioned earlier the fact about the halos moving through the IGM and the kind of numerical effects that might induce. There was a really nice genetic modification paper. I forget who the authors were, but I just remember it was using genetic modification where from 6 months ago or so,
Nicole
where the
Sanchez?
change. perhaps the change that they made, it was about dwarf galaxies, and the only change that they made was what is the velocity of the galaxy that they were focusing on with respect to its surroundings. And when they made the change to basically make the galaxy at rest with respect to the box, if you will, they found much sharper features, much more cold gas. Everything was a lot less fluffy. So that is an important effect, which is very often, I think, especially for satellite galaxies or streams or stuff like that, is just ignored even in our numerical conversations.
Yeah, that was from the Chonga gasoline group. I forget the first author. He's in the UK. But yes, yeah, that's about
Andrew Ponson.
Yes, Andrew Ponson.
Yeah,
Yes,
yeah.
thank you.
Let's have Miao Lee has her hand up. Let's hear from her.
Yeah, so I was looking at the chat window, and I think Kirill there posed a very, very helpful point. That is the subgrid model, the feedback model that, in those cosmological simulations. I mean, thinking of precipitation, it happens, the feedback, the outflow, and also the pre-existing gas in the halo. And I think the subgrid model matters for both points. I mean, for outflow part, what I'm talking about is the hot outflow that, you do need a certain condition, for precipitation to happen. If, say, the hot outflow is too energetic, then you can imagine that, before it can cool, it just breaks out of the halo sort of in a spherical way, so it has no chance to cool. Therefore, you may not observe this precipitation. On the other hand, if the hot outflow is too weak, then it doesn't really propagate into the halo. So you also don't see, it's not even emerged from the disk not far, then you may also, not able to, observe this precipitation in cosmological simulations. So this is for the outflow part. The other part is the pre-existing gas. It's sort of the accumulation effect of, outflows over, cosmological time. So in that sense, the halo may not have the right amount of pre-existing gas when this new outflow is emerging. So that may be another, factor that's, goes into that not observing this precipitation in cosmological simulations.
Okay. I think, we are talking a lot about precipitation here, and I kind of want to shift gears. And Crystal has a really nice question, and I want to see if she would like to ask it about dwarf galaxies and core collapse supernova propagating feedback through them.
Sure. Thanks, Ben.
Yeah.
I really like this stained glass window picture that Greg presented. And, at the end of his talk, you got to the lower mass galaxies, but then we kind of jumped all the way down to 10 to the 6 solar mass halos. And I thought the region of that plot in kind of 10 to the 9 to 10 to the 11 solar mass halos looked very interesting, because like the dividing line for the supernova feedback was very steep, so that at 10 to the 11 solar masses, a lot of the halo was affected by the supernovae. But by 10 to the 9, your R over R veer there for the supernova feedback, it was like 10% or something. It was a small amount. And I was a bit confused then. You showed the Pangea simulations and were saying that, I guess that was 10 to the 10 solar masses or something, and the supernova were going through the whole CGM. But is there something that happens at these lower kind of 10 to the 9 solar masses where the supernovae don't get there because there's just not enough stars or something? Or is there some big transition that we should expect in the CGM between 10 to the 9 and 10 to the 11 that as observers we could go look for?
Yeah, I think that's a really great question. Just one point of clarification. So I quoted a number for the first star stuff as 10 to the 6 solar mass halos, but I just want to say that the connection. I mean, what's important is the virial temperature, and the connection between mass and temperature has a redshift dependence. So really, since those are at high redshifts, those correspond to effectively at low redshift, they would be much more massive systems. The interesting transition there, of course, is where the temperature, the virial temperature, gets down to about 10 to the 4 degrees. And at that point, then the cooling properties change quite a bit. So the stability of the gas depends on the steepness or the dependence of the cooling function on temperature. So when it's rising like that, that's thermally stable gas. So those very low mass halos have potentially thermally, if they're low enough, they're thermally stable, and so that then moves towards a picture which might be look more like a classic cooling flow that, for example, Jonathan Stern was talking about, in which there is no condensation or precipitation, and you just get cooling at the very center of the halo. And in fact, I think you saw something like that happening in some of the fire simulations, and we've seen similar for the lowest mass halos. So in terms of observational predictions, I have just started to think about that. The gas densities of those halos are typically quite low, because of what I talked about beginning. The supernova feedback can easily remove gas from those halos, and so they're hard to observe. But on the other hand, they're temperatures which are quite observable, 10 to the 4. So I haven't made any concrete predictions. I would be really interested in hearing from people who have thought about this.
That sounds like I know Mary Putman's on the panel, and she observes sightlines around dwarf galaxies. But I see Sijing's hand up. So
I just wanted to add a little bit. Just so I completely agree with the picture that if you goes down below 10 to the a few times 10 to the 9, then the virial temperature is pretty much close to the IgM temperature. But for this little system, actually, from my very limited sample of little dwarf galaxies, it is very, very stochastic. So this is kind of echoed the point that Annalisa made yesterday, which is more massive system, how environment can affect the satellites. And this exactly the same thing happens to the dwarf galaxies, even for the cases which we will call as few dwarf galaxies. So in one of our recent studies of just few dwarf galaxies, so there's no Milky Way kind of big massive things around. If you have a few, just 10 to the 10 of just above 10 to the 10 halo mass of dwarf galaxy around, and then the CGM created by those supernova explosions within this 10 to the 10 halos can affect the nearby 10 to the 9. The formation of the nearby 10 to 9. So there's two effects here which we observe. Is one is that if you have gravitational interactions that can actually promote the gas accretion coming into the little dwarf galaxies, so the 10 to 9 galaxy, which promotes sort of ignites star formation. It doesn't last very long. You have a peak and then it's gone. No, that happens. And on the other hand, if you have really CGM created from the more massive galaxies, then it will quench the formation. It will quench the star formation completely from the little ones. And this is actually really sensitive, to my surprise, to the subgrid models. So we have tested two subgrid models. One is, the delay cooling approach. So you have ballistic sort of wind come out and you delay cooling a little bit, and then you let the wind go. And the other approach is the so-called the super bubble approach, where in the main point is that the wind or the CGM have a higher entropy. So in the first picture, you will see that you have the metals spreading everywhere, all the way to megaparsec even. Okay, and you have to have that velocity to eject those mass to get this, stellar mass halo mass relation. So it's kind of spread around kind of picture. And the second picture with a super bubble, you have the high entropy. So the gas is sort of just around there with high entropy without being dispersed very much. And then when your little dwarf galaxy came in, the interesting happened is that gas accretion into these little dwarf galaxies is suppressed. So it's some sort of starvation going on for this little dwarf galaxy, and it doesn't form at all. So in the low mass system, I would say this is really complicated. Depends on what kind of environment they're in, and this is also the same case for high mass galaxies, of course. But observationally, I don't know. I would really be excited to hear some opinions from observers. What kind of things we can probe. We've looked at the column densities and stuff, but that seems to be okay. But more diagnostic way to tell the difference would be nice.
Kirill has his hand up.
I guess on a related note, one moment, my sound is being weird.
Oh, we've lost you.
Yeah, we
How
can
about
hear
now?
you. Oh, now
we can hear you.
Yeah, headphones doing weird things. To what extent, sorry, right, so we can talk about predictions for a general tendency, right? And I think that is kind of what a lot of the predictions for more massive galaxies have been, right? You predict a typical amount of oxygen 6 or a typical relation between, I don't know, right, like the line width of something and the column density of something, et cetera, right? Or, amount of hydrogen versus distance, amount of X-rays versus distance, right? But basically central tendencies. And so if it's true that there is a scale at which you switch over to being extremely stochastic, would it make sense to look for that scale, right? And basically to make predictions for a scale at which, the variance of properties should blow up, right? Because if it's true that dwarf galaxies are extremely stochastic systems, then this stochasticity should be observable somehow, right? And it's observable perhaps in star formation rates, but can it be observed in the CGM as well? And can people make predictions for the scale, let's say, at which you go from, just knowing that something is a dwarf galaxy isn't going to tell you much about exactly what you expect to see, to knowing that something, is a bit more massive does tell you something about what you expect to see.
Wow.
Ben,
I love Kirill's cat. Look at that. It's that cat is paying attention. Joe, go ahead.
Wait, Mary was about to say something.
Mary, great. Yeah, I'm sorry, Mary.
I guess our panel members supposed to raise their hand? I've kind of been unsure on how.
Yeah, either way, you have prerogative, though. Go.
Oh, well, in that case, no. I actually mainly have questions, to be honest. I don't think that, I actually think observers, like Jess was asking, are looking to you a little bit to say what you would expect to observe. I mean, we do have some observables, but we're not sure what it fits. So we're just trying to sort that out. But Sijing, I'm wondering if one prediction from what you're talking about, and it sounds like most of this would be happening at higher redshift, and also that, Greg, this is related. I want to ask you about the model where you have the expanding the gas staying hot and going out into the IGM as well, which sounds along the lines of what Sijing was saying, is whether you would expect then for dwarf galaxies to have little gasless dwarfs around them. And is that a clear observational prediction? And in terms of what we've detected, we're somewhat limited, of course, because then you're talking about gasless little blobs like we have around our Milky Way, with not many stars. But, the Magellanic Clouds, now we think there's a bunch of those small little blobs that possibly came in with that. And then I think we are starting to get to those kind of depths going out to the nearest gas-rich dwarfs. And so far, there's not a lot out there. We definitely see gas dwarfs, but so I'm wondering, would you say that's a clear prediction of your model, that you would expect that you would find quenched little dwarfs around dwarfs? No?
No. In our simulations, I mean, these are still star-forming dwarfs in the end of the day. I mean, not the. I think you were talking about the one that is actually formed stars, right? Not the one that has been not formed at all. So there's dwarf galaxy.
No. Oh,
yeah.
so this is so high a redshift it hasn't formed at all?
No, so the situation is that for 10 to the 10, we still have a lot of supernova ejections, and we eject a lot of gas and a lot of metals, but the dwarf galaxy itself is still gas rich because the ratio between the gas and stars are still very high. It's quite high in the case, at least it's 1-to-1 or even the factor of few more times gas compared to the stars. So they are can be characterized as gas-rich dwarf galaxy rather than gas poor. But the ones that got quenched completely, which
that's what I'm talking about. I'm not talking about the main one. Yeah.
The main one.
Okay.
Yeah,
but
it's already
the main one would have little quench things. Is what I'm asking.
The main one you're talking about, right?
No, the main one, yeah, I understand. The main one would be a slightly larger dwarf galaxy, probably gas and star forming,
right.
But that it would, based on your description, have little quenched, smaller dwarf galaxies near them.
Well, yeah, I actually haven't looked at how much gas. It's not completely gas-free. It definitely has some gas in it, but I haven't really compared with the gas ratio, to normal cosmic ratio exactly.
Okay.
So I think they are relatively gas poor because gas has trouble to come in, but they are not completely gas free, unless they are going to also another environment effect, which is the RAM pressure stripping. So if they fall into the more massive galaxy, even it's just a little bit more massive, the stripping still kicks in, so the gas fraction goes low. But other than that, they have the gas fraction normally, not very poor, I would say. That's but I haven't really looked at it in detail.
Okay. And Greg, related to that, I'm curious, how long does this heating, that you seem to indicate that the virial temperature, it stays at the virial temperature, so there's basically a continual heating going on and a continual heating out to quite large radii, which kind of puzzled me.
Yeah, puzzles me too. So I don't have a good answer for what in these simulations. I mean, clearly, you can see from the from both of these that there's for these low mass guys, there are regular shocks which go through. But part of the heating may be, if it's a true cooling flow, it may just be compressional heat as these things flow in.
Okay, well, I do think, like you said, I think the problem is the densities are so low. Observables are going to be tricky, but it definitely sounds like it produces some clear predictions.
Yeah, I think we don't have, I mean, at least I don't have those predictions yet. I think you would need to do some simulations, but I think it would be, really interesting to try and do that, to look at, various, as you suggest, correlations between star-forming properties of galaxies of different masses at the low end.
And I think because it's so stochastic, we need actually a lot of those simulations to actually get proper scatter.
For Joe Burchett has a point that there is data at low halo around dwarf galaxies in the CGM, and I'm going to have that conversation continue on Slack, where you can hit him up. I know it's 10 o'clock, but I see Pratik's hand up, and let's give him the last word here.
He's got the answer. The answer.
Yeah. Yes. Sorry about that. So the resolution. So in my mind, there are two very broad classes of. One is the existing big cloud, and you grow multi-phase gas in its tail. So, RAM pressure tails of galaxies or ISM chunks lifted in hot galactic outflows and IgM filaments penetrating the hot CGM are in this class. The other class is when multi-phase gas condenses out of the hot diffuse CGM with delta rho or rho small, or order unity or largish, but no dense gas present. So so once cold gas condenses in precipitation 2, it forms a dense clump which falls through the CGM. So the precipitation model gets quickly converted into growth question, right? So that you cannot really separate all these very cleanly into one another, but precipitation or thermal instability model is useful because it gives like a very nice upper limit on the state of the hot gas, right? So that is what I think Mark is saying about the global value of this precipitation. But of course, the reality is so complex that this cannot be the answer for almost everything. There has to be a lot of knobs and other things which are more dominant in different situations. So that's my take on it.
Okay, thank you, Pratik. That was worth it. All right, that was an active session today. I like that we got to talk about both high mass halos and low mass halos. And again, thank you to Greg for covering all galactic halos that we study, and to the panel. I am